water.
Okay.
I looked at the solutions manual and they just said 100 milliliters, and then they just converted that to liters. Yeah. I don't know where to get the 100 milliliters from.
Number 46?
Yeah.
Okay, cola drinks have a phosphoric acid content that is described as, estimate the pH. We don't need volume for this at all.
We don't?
No.
Okay,
But, you don't have to be given the volume, but you have to know about percentages. So let's take a look at this.
alright. I'm ready for this. Actually, I'm waiting for you.
All right. So 0.057% of 75% phosphoric acid. Okay, so this is the low end of the concentration. The high end of the concentration is 0.084%. 35% H3PO4. And so this is just a problem for figuring out the molar concentration. And so what is the molarity of these solutions? And so what you have to do is we have to go from percent by mass to molarity. So this would be something similar to something you would see in chapter 12 or 13. Chapter 13.
But the thing is, I don't know where they got the 100 milliliter from.
All right, this is the cola. And so, what does a percent mean here? This 0.057% means what? It's by mass. And so, what that means is 0.057 grams of 75% H3PO4 solution per 100 grams of cola.
By mass.
By mass, right. And so in this, what we want to do is we need to figure out how many grams of phosphoric acid there are. And so what we're going to do is we're going to use a little bit of dimensional analysis to solve this. And so if we know how many grams of the 75% phosphoric acid solution we have, then we know that for every 100 grams of 75% phosphoric acid, we have 75 grams of pure phosphoric acid. So are you okay with this so far?
Yes, I get this part, but I don't get the bottom part.
Okay. So this is going to give us grams of pure phosphoric acid because the 75% solution will cancel out and leave us with pure phosphoric acid. Then we convert the phosphoric acid into moles. How many moles of phosphoric acid is that?
About 98 grams.
Okay, what is it to more sig figs? Did you calculate it to more sig figs?
98.07.
98.07? Okay, so a mole of this is 98.07 grams phosphoric acid. Okay, so now we get rid of the grams of phosphoric acid and we're left with moles of phosphoric acid. But we want molarity.
Yeah.
And so we have to make an assumption.
Why though?
We have to assume the density of the cola unless they gave it to us, but they didn't give us the density of the cola, so we're just going to assume the density of cola is close to that of water. What's the density of water, roughly?
1 gram per milliliter.
Yeah, this is not a good assumption, but we're going to have to do this, and otherwise we can't solve this problem. Unfortunately. So assume the density of the cola is about equal to the density of water. And so we'll have 1.00 grams per milliliter. And so the grams of cola cancels out and gives us milliliters. And molarity is in terms of liters, so there are 1,000 milliliters per liter. So that'll give us the molarity of the phosphoric acid.
But where the heck did it get 100 milliliters?
I don't know. I need to see the solutions manual. You have a picture of it? All right, I see where they got it. Actually, let me look at that one more time. Sorry, I need to look at it. All right. This is what your book did in the solutions manual. This is 100. This is 0.057% by mass. What the book did was the book did this and they skipped a step. The book assumes that the density of the cola is about the same as the density of water. And therefore, what they did was they converted this from 0.057 grams per 100 grams to 0.057 grams per 100 milliliters.
Okay, that's where they got it.
Yeah, they're saying that each gram of cola is a milliliter of cola. Does that answer the question for them?
Yes, that's good.
That's what they did. Okay, they just went ahead and they just changed it from grams into milliliters, like this. Because if you have 100 grams of water, that's 100 milliliters. So they just said, well, if you have 100 grams of cola, that's 100 milliliters. That's all they did. Okay.
For the density, if the density is not given, should we always assume that the density is equal to that of water?
Yeah, for a solution. Okay, are there any other questions?
33.
All right.
Exam, are we going to get a chart, or is your exam going to be structured in a way where everything's given to us and we don't have to find out like values?
No, you might have to find some values,
Okay.
either on the board or on the exam itself.
Okay.
Number 33?
Wait, no, number 32.
32?
Because I posted this on Piazza.
I missed it then. A saturated aqueous solution of orthonitrophenol has a pH of 4.53. What is the solubility of orthonitrophenol in water in grams per liter? 32. So orthonitrophenol is an acid. And it has a pKa of 7.23, which means the Ka is, we got to reverse this, 10 to the minus 7.23, which gives us a Ka value of what? .9. Oh, is it 5.88? Let's not round it. Let's use it. 5.88 times 10 to the negative 8. So what they want is they want us to list the solubility. What that is this. It's going to be the initial concentration here. This is the unknown. We want the total, you know, it doesn't matter what species it splits up into. We just want the total amount of whatever, in this case, orthonitrophenol in this mixture.
We don't know the initial concentration.
Right, and so the problem is to try to figure out what the initial concentration is. So we need to be given something. So we know this is going to be minus X, this is going to be plus X molar, this is going to be plus X molar. And then we have the initial minus X molar, and then this is going to be X molar, this is going to be X molar. Yeah, we have two routes we can do here. This is a monoprotic, so this is step 1. We can incorporate step 2, or we can ignore it. And so 1 is we go down to step 2. 2 is we ignore it.
How do you know the perfect way to go? How do you know the perfect way to go?
How do you know the perfect way to go? We just guess. Which one do you think is going to be easier? Ignoring step 2 or factoring in step 2?
Ignore.
Ignoring. Otherwise, we got another ice table and we have to add, right? And so what we're going to do is we're going to ignore step 2 and then see, would step 2 have been a significant contributor to hydronium? And so if we ignore step 2, then X is equal to the total hydronium. If we don't ignore step 2, then the total hydronium is equal to X plus Y. We'll call Y the additional hydronium we get from water. And so we'd have the hydronium from step 1 plus the hydronium from step 2, right? And then we got 2 unknowns. But anyway, let's ignore it and see if it's okay. And the way we see if it's okay is this. We know what the total hydronium is. The total hydronium is equal to 10 to the minus pH. They give us the pH because when you stick a pH meter into this solution, it measures the total hydronium. It doesn't measure, you know, how much came from step 1, how much came from step 2. It just measures the combined hydronium. The pH is 4.53, and so this is 10 to the minus 4.53 molar. And so what does that come out to? 2.95 times 10 to the negative 5. Fine. All right. If we assume that all the hydronium came from step 1, this is the amount. Now, when you look at this amount, how much hydronium could we get from step 2, Kw, max? times 10 to the negative 7. So, and it's going to be less because of the common ion effect, right? And so the most hydronium we're going to get from water is going to be less than 10 to the minus 7. Would 10 to the minus 7 molar have an impact on this? No. And so this is how we do it. We assume we could ignore it and then check it. If this comes out to 10 to the minus 5, good. No problem ignoring it because y here is going to be no bigger than 10 to the minus 7. That would be y. Does that make sense without writing it all out? Yeah? Now, if this came out to 10 to the minus 7, would you ignore step 2? If this came out to 10 to the minus 7, then we'd have to incorporate step 2 and we can't ignore it.
Because it's a significant contributor?
Yeah, because if you only have 10 to the minus 7 molar hydronium to begin with, then water is going to be significant. What if this came out to 10 to the minus 8? Do you remember 10 to the minus 8 molar hydronium? You should remember that from 10 to the minus 8 molar HCl. Could we ignore hydronium from water? No. And so if this came out to 10 to the minus 8, then we're in trouble. We have to do step 2. And we have to figure out what x and y are, not just x.
Okay, but how about if this comes out to be negative 10 to the negative 11, for example?
Then for sure, Kw is going to be a huge contributor. What if this came out to 10 to the minus 2? Then not significant at all. And so this is the way we do it. If you don't know, then you just have to do step 2 also, which means another 20 or 30 minutes on the problem.
Uh-oh.
Maybe less. I mean, once you don't want it, it's not that bad. It's actually not that hard to incorporate step 2 in here at all. All right, well, let's just finish this. So this is x here. And so we plug that in, and then we figure out what these others must be. In other words, we got to figure out what this is. And so we will plug it into this equation here, which is the hydronium times this anion divided by the acid, which I'll just call H dot dot dot. It's going to come out to 2.95 times 10 to the minus 5 squared divided by the initial minus 2.95 times 10 to the minus 5. All right.
Okay, y squared.
Yeah, x times x.
Okay.
All right. And so here, there are two ways. This is not hard to solve, right? So you can solve this without making assumptions, or you can just go ahead and guess that the simplifying assumption is going to work and then check it. Yeah. If the simplifying assumption works, then this is even easier. If it doesn't, then it's still not hard, the math. You don't have to do any successive approximations or anything like that. Okay. All right, is that enough, Kelly, to solve?
Wait, but the ultimate goal is the solubility.
Right, and so this is a saturated solution. So this is maximum molarity. And so what you have to do is you have to convert it from moles per liter to grams per liter. And so you just have to multiply it by the molar mass.
Well, what's the molar of that? What's the molarity of the initial?
That's what we solve for. We solve it right here. We solve for this, which is called Z. That will be the molarity of the initial. And so that would be the maximum number of moles that you can get in per liter because it's saturated. And so you got to figure out how that many moles weighs how many grams. And so you just convert moles to grams.
Once you, what if you don't know how to solve for that?
Solve for what?
That initial right down there.
You just multiply both sides by this. Right? So
Wait, multiply each side by the chromium?
by this down here. so we'll take, this is Ka, right?
Yeah.
And so this is going to be Ka, which we know what it is, times the initial minus 2.95 times 10 to the minus 5. I would have used the simplifying assumption here. This is equal to 2.95 times 10 to the minus 5 squared. If you use the simplifying assumption, then this initial is just equal to this divided by Ka. What did you get it, Andrea? What did you get?
1.47
Times 10 to the negative 7?
7.
Times 10 to the negative 2? Oh, then the simplifying assumption wouldn't have worked. So you would have had to solve this.
Yeah, that's fine.
You solved it, okay. All right, that's the molarity. So this is moles per liter, and then you just take the molar mass, cancel out moles, and get it in grams per liter. That's it. Then you would be done.
This is solving for the initial concentration. It's kind of hard.
Yeah, that's it. That's good.
Can you explain number 69?
Wow, you got that far?
All right, let me just say something. I decided for molecular structure and acid-base behavior, we're not going to skip it. We're going to do a lab on this. So I'm not going to test you on this on Thursday. Yeah, if you already did it, did you already do it? You could turn it. You don't have to, yeah. You did it? Well, we'll take a look at this though. 69, I did this in Chem 1A, but you guys didn't do this in Chem 1A. Is that it? Okay. Yeah, you didn't. So, 69, so it's actually, I just gave the same homework assignment I gave in Chem 1A for this part. But let's take a look at this one here. From the following bases, select the one with the smallest Kb. And so the way KBs work is the lower the Kb, the weaker the base.
So I know A is going to be a little bit, so we most acidic.
And one with the largest Kb and give you the reasons, but we don't want to think in terms of acidity. We want to think in terms of basicity. These are all amines. And so what makes one base stronger? And if we look at these could have acid sites as well, but we're looking at the base behavior, which means we have to look at the base site here. And so what is causing this to be basic? What's causing it to be basic is this nitrogen. This nitrogen is in a bonding environment. Here it's bonded to 1 carbon and 2 hydrogens. Carbon and hydrogen have approximately the same electronegativity, 2.1 versus 2.4. And so that means this is very much like ammonia, in terms of electronic environment. And so here we look at this, and then these, C and D, and we see it. And so all these have 2 hydrogens. So the only thing is what we call the R group. R group is just some rest of the molecule. It's going to have a carbon or hydrogen. And so what makes a good base is its ability to donate this electron pair. And so the bigger the delta minus on this, that is the more negative charge density, the better the base. And so here, increasing delta minus means increasing basicity. Let's just say base strength. Which means increasing Kb. And so we have 2 types of R groups here. We have the types of R group that suck electron density away, kind of electron poor. And we have electron-rich R groups which push electron density. And so the more electron-rich the R group is, the more basic this should be, and the more electron-poor this R group, the less basic it should be. Depending on if it sucks electron density out, it's going to make this delta minus smaller. If it pushes electron density in, it's going to make the delta minus bigger. And so what we have to do is we have to look at the R group and then look at whether it is an electron pusher, that is, it's pushing electrons onto the nitrogen, or an electron withdrawer, it's sucking electron density out from the nitrogen. Yes, Kelly?
Okay, how do you know which R groups are electron rich and electron poor, and how do we calculate delta minus?
Okay, the first question, how do you know which, you use the tools you learned in chapter 3. Chapter 3, all right. Chapter 3.
I forgot, what was chapter 3 about?
Structure and properties. That's too vague, obviously. I don't know. How do you figure it out? So if you look at these two things, how do you figure it out? Well, there are different levels we can figure this out. We can do a full structural analysis. This is what we did in Chem 1A. What we do is we look at the charges on the atoms. Now, how do you figure out what the charges on the atoms are? There are 3 ways to determine the charge on the atom, right? What are the 3 ways to count electrons on
That's
atoms?
old-fashioned formal charge.
Formal charge, that's not in chapter 3. Formal charge is like in chapter 9 or 10. All the formal charges are 0. And then we have the oxidation state, which is in chapter 3. That's going to tell us what it is. We look at the oxidation states on each individual atom, and then we can determine it quite easily. But anyway, we don't have to do that because let's say you forgot chapter 3. There's other ways of doing this. The other ways of doing this is, you know, in terms of electronegativity, chlorine versus carbon. Chlorine is much greater electronegativity, right? It has electron sucking. It's pulling electron density to it. And so if you have a chlorine, this is a benzene ring, versus a carbon on a benzene ring, it appears that the chlorine will be more electron withdrawing, making this species here less basic or more basic.
More.
If this is sucking electron density, this is going to make the delta minus smaller, making it less basic. And so just based on chlorine versus methyl, chlorine is going to be more electron withdrawing, therefore I would expect this one to be less basic, and this one should be more basic. But then we got C and D. If it were only A and B, then we're done. It's easy, right? But C and D are going to complicate things because it's not a benzene ring anymore. There's more to it. And so let's take a look at this next group here.
What's the name of
A?
Yeah.
Well, in organic chemistry, you're going to learn about this. You know, we look at the benzene ring, and the parent would be this. This is a more important group. And so this has a common name. This would just be called aniline here. And then we have certain positions. This is the ortho position, this is the meta, this is the para. So this would be like orthochloroaniline, something like that. And so we can name things based on that. But you don't have to name these. And then this is the propyl group. So this is called propylamine. This is some other group which doesn't have a simple name. So this would be more complicated name. And so we try to figure out based on these groups, you know, how much electron density is there. And since we can do that by using different things. So what we look at first is the bonded atom. If that doesn't tell us, then we look at the next nearest neighbor. If that doesn't tell us, we look at the next nearest neighbor. And so the easiest way to analyze this is just by using oxidation states, probably. And so when we use oxidation states, well, let's just look at the first one via oxidation states. And I'm going to write out the full structure. Since this is okay, there are other things we can do as well, but let's take a look at this. So what's the oxidation states on, what are the oxidation states here? What's the oxidation state on nitrogen? The oxidation state on this nitrogen is? Formal charge would be 0. Oxidation state is? If this were a review, then yeah, I put this on the test and we talk about it briefly. But judging from people's understanding of oxidation states and this type of stuff, this is going to take much more time than I want to spend right now. When we do the lab, then I'll do it, I think, because then we'll see it structurally. The oxidation state's -3. This is +1, +1. This carbon, what is the carbon here? Well, it's got 1, 2, 3. It's supposed to have 4, so it's +1. And this carbon, 1, 2, 3, this is going to be +1. This is going to be -1 for the chloride. Okay, this is going to be 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, it means it's -1. This is 1, 2, 3, 4, 5, -1. This one's going to be -1. This is going to be -1. This is going to be +1, +1, +1, +1. And so we look at that. Well, so this is that structure. Then we go to the next structure, and then we take a look at that and see if that tells us anything different or tells us the same thing.
How can oxidation states tell the difference in the basis of?
Because they give us an idea of how the electrons are distributed. In other words, electron density is distributed in the molecule. And so, for example, if we compare it with the other one, with the methyl group on the end, it's actually a lot more complex, a lot more complicated because I'm skipping some stuff. Skipping some stuff that we'd also look at. But it's just as far as making a simple comparison between two molecules, we see, does formal charge tell us anything? No, it doesn't tell us anything because nothing changes on the formal charge. The formal charges are all 0 here. Well, then we look at the oxidation state. So the oxidation state's telling us anything. So this is 1, 2, 3. And so this is +1. No, it looks like it's the same, right?
Mm-hmm.
Looks like it's the same, but when we get to here, 1, 2, 3, 4, 5, this is -1. This is -1, -1, -1, -1. This is +1, +1, +1, +1. This one would be 1, 2, 3, 4, 5, 6, 7. So this is -3, +1, +1, +1. Now, looking at the two groups, we call a chloro, this is called a chloro, by the way, we call a chloro electron withdrawing. Do you see? Because it's got a +1, it's going to suck electron density out of the ring. Do you see? Whereas methyl is the opposite. Methyl is called an electron pushing group because that's rich in electron density, it pushes negative charge density into the ring. And so this one's going to be much more basic than you'd expect for this one based on the what we call the substituent group on the ring. Now the position makes a difference. Whether it's ortho, meta, or para is going to make a difference due to resonance forms that we can generate, but we aren't going to talk about that because that's going to be saved for later when we talk about the lab. We'll talk about all that stuff. Okay.
The lab? Wait, well, isn't that the lab on Thursday?
No, it's a computer lab. We're going to use a quantum mechanical program called Spartan. I don't know if very many have used it.
So computer.
I know Veronice is using it. What's that?
So computer and then test? We're going to go to computer lab and then we'll have our test?
No, this is way in the future. In the future. The first time we use Spartan, this is going to be a repeat of the 1A lab. And so I was thinking, rather than repeating it for 1A students, my 1A students, I'm going to have my old 1A students do bases rather than acids. Make it different than and then the people who are unfamiliar with the program do acids. Okay.
That's interesting.
But yeah, you would just you know, that's if you buy a computer software program like Spartan, which costs maybe $5,000 or something,
Damn.
then you could do this easily, you know. But what if you don't have a $5,000 software program like Spartan? How would you figure it out?
We gotta use our camera.
Well, this is free. I mean, calculating oxidation states doesn't cost any money, so you could do that free, right? And then kind of figure it out based on this type of stuff.
So how did you get the negative 3 for the carbon?
How did I get the -3 for the carbon? Winner take all. So hydrogen versus carbon, carbon wins. Carbon versus carbon is a tie. So 1, 2, 3, 4, 5, 6, 7. 7 electrons. It's supposed to only have 4. It's got 3 extra electrons, so -3. That's how I got it.
Winner takes it all.
Yeah. Winner takes all. But you know, this is not counting oxidation states like this is not in the book. This is you know, this is just another way of counting it. So since it's not in the book, and
So do we skip 68, 69 on all of them?
yeah, skip those. Skip those, and we're going to come back. So, for those particular ones, we're going to look at it in greater detail. Okay, other questions?
Not
So
for me.
what you could do is you could go through the others, you know. What was that, number 69? Okay, when we go to something like a propyl groups are electron pushers. When you look at the oxidation state on this carbon, it's actually negative, whereas in this carbon, it's a somewhat electron withdrawer here. And so this one's going to be, should be even more basic. And then we go over here. Well, having the nitrogen there is going to withdraw electron density this way. So that's going to have an effect, making this one less basic. So you'll see it, because then you consider it, because these two oxidation states will be the same, and then you look at the next one's totally different. And so that next one's going to have an impact on that one, which is set up like a chain type.
So
reaction.
the general trend is the more electronegative, the more basic.
No, that's wrong. That's wrong because, let me ask you this. Which one is more basic?
From this point, I don't know.
Okay, you said the more electronegative is more basic. Well, the more electronegative, the more electronegative is fluorine, right?
Yes.
It's more electronegative than chlorine, but this one's less basic. This one is less basic because this, you know, the oxidation states don't tell you anything because both of these have the same oxidation state. Then we have to look at it more deeply. Because if oxidation state doesn't tell us, we go to the next level. And the next level would be, well, even though this is -1, this is -1, they're different because this one is more electronegative. And so this one's going to suck more electron density away from the nitrogen. This is going to suck less electron density away from the nitrogen. And what we're looking at is the delta minus on nitrogen. And so this one will have a bigger delta minus on nitrogen. This one will have a smaller delta minus. And so this one's less basic. But wait, then you might say, oh, then it's simple because the less electronegative is more basic.
Yeah, I might think that.
And then it's wrong too because, you know, there's another example here. Well, what's more electronegative, oxygen or sulfur? Oxygen is more electronegative, sulfur is less electronegative. So you say, okay, the less electronegative is more basic. Well, that's wrong.
Okay, what's the trick
Oxide.
here?
So you can't come up with a simple rule like that because there are too many exceptions that you have to, and so account for, and therefore never think that way. When you think about a base, you think about the negative charge density on the basic atom. And what impacts the negative charge density on the basic atom? And so a lot of people, you know, and Petrucci's guilty of this too, because Petrucci says that, he says something like this. He says that oxide is more basic because it's more electronegative, but that, you know, if people memorize that, then they're going to get this one wrong. You know, and so you got to be careful. And then so what you want is you don't want a simple rule. You want to understand it more structurally.
Okay, then that leads to this question.
Okay.
What will make this more basic than that?
Well, that's what we're going to do in the lab. We're going to look at this in more detail in the lab. When is that lab scheduled? Does somebody have the syllabus? It's called the Spartan Acid Lab. I think. Well, I don't. Let me just see. Computer acid strength. So yeah, I did I grouped all the computer labs together, but really we should be doing this acid strength lab earlier. It's Chem 108 Computer Acid Strength Lab, and there we're going to look at it because you're going to do this by hand to make your prediction based on as much stuff as we can figure, and then we're going to use the computer to tell us that. Also, maybe I should have done, Visual Mentech should be after chapter 18. And so these two labs are a little late, especially the acid strength lab. But we'll get there eventually.
Those are going to be really interesting.
Yeah, Visual Mentech is an eye-opener.
So, the higher the delta minus on the conjugate of the acid of the base, does that increase its basicity?
Wait, so what's the point? The S minus? Like when it increases? It's getting more basic?
Yeah, and just the opposite, for acids, you want a bigger delta plus on the hydrogen. That makes it more acidic. Yeah. All right, any other questions? Uh-huh.
Are you able to post an exam and audit?
Yeah, this afternoon I'll post it. I didn't bring my computer today, so I have to wait. It's on my computer. Okay. So look. Okay, any other questions? Where did we leave off last time? Were we looking at ions? Spun. Stepwise for which one?
Monohydrogen phosphate.
Monohydrogen phosphate. Oh, were we doing the amphoteric species? Okay. So amphoteric basically, it ends up perturbing everything. The amphoteric is a special case. And amphoteric, was it dihydrogen phosphate or monohydrogen phosphate? Dihydrogen phosphate? You know, dihydrogen phosphate can hydrolyze or collide with water to form hydronium, or it could hydrolyze with water to form hydroxide. So it can go both ways. And so what we learned here from this particular problem is that this has to be solved simultaneous, because there's going to be Kw tied in here. And so we have three equilibria that must be solved simultaneously. Right, but this is a special case because of the fact that the acid and the base are the same species. And so there's, you know, since the acid and base are the same species, there's some simplifications that can be done. And so when you do this simultaneously, you know, and then we assume two things. We assume that, one, the initial concentration is significant. And two, the SA works, the simplifying assumption works. Then we end up with this equation, that the pH can be determined by taking the pKa of the amphoteric plus the pKa for the conjugate acid of the amphoteric. Did I already write this on the board? Or not? No? Divided by 2. Yeah. And so it's what happens when you solve this simultaneously and make some simplifications, then the pH comes out. We aren't going to figure out what the species are because this would be too much work. All we're going to do is we're going to determine what the pH of this solution is. And so if I have something like this, let's say I have 0.100 molar sodium dihydrogen phosphate, and I want to figure out what the pH is, I don't have to do Ka, Kb, and Kw simultaneous. All I have to do is just plug it into this equation. And so I need the pKa of the amphoteric species, which would be H2PO4-, plus the pKa for the conjugate acid of the amphoteric. What is the conjugate acid of H2PO4-? H3PO4. No, it's this equation comes from all the math that came out of here. So it's just how it works. It's not redundant. Divided by 2. And so the pKa of H2PO4- is, actually we could look it up. All right. Well, actually, I know the number. It's 7.20 is pKa. And then the pKa for phosphoric acid is 2.15 divided by 2. So this comes out to 9.35 divided by 2, which is 4.675. All right, so that's a special case. We have that. Amphoteric. Did I talk about cations and anions in general? No, let's talk about those now. Ions as acids and bases. Cations are normally acidic, so let's look at ions. It's just a metal cation, sorry. Metal cations are acidic except group 1, and calcium, strontium, and barium. Group 1, calcium, strontium, and barium are the cations for the soluble hydroxide. These are neutral. The sodium ions would be neutral, potassium ions, calcium ions, strontium. Whereas if we had aluminum ions would be acidic. Iron ions, acidic. Yeah.
What is the first? I can read before calcium. So what is that?
Oh, group 1.
Oh, okay. Well.
Group 1 and calcium, strontium, barium. All right, anides. Strong acids are neutral. Except HSO4 minus, which is acidic. So chloride. Chloride is, you know, this is a base. This is the conjugate base of HCl. But there's a conjugate relationship. If HCl is a very strong acid, then chloride must be a very weak base. It's so weak that you consider it neutral. Chloride is neutral. Bromide, nitrate, etc. These are all neutral. In other words, the conjugate base of a weak acid is so weak it's not basic, it's neutral. Except for HSO4 minus is a very weak base. We consider it neutral as far as base properties go, but it's amphoteric, so it's an acid. So let's look at the pH of ion-containing solutions. We do this qualitative and quantitative. So let's look at it qualitatively first. Something like sodium acetate. Is that basic, neutral, or acidic? Basic. Sodium ions are neutral. Acetate is a base, so the pH is less than 7. Quantitative, you know, what would we do? If we're looking at this quantitatively, then we do Kb for acetate. It's going to produce some acetic acid and hydroxide. So we have Kb and Kw. And we can figure out what the pOH is, and from the pOH we can figure out what the pH is. That's what we do.
Wait, if it's basic, shouldn't the pH be greater than 7?
Oops. No, not less than 7. You're right. pH should be greater than 7. Ammonium chloride. Ammonium is acidic, chloride is neutral. So the pH should be less than 7. And so here what we do is we do Ka and Kw for quantitative. If it's pH, you know, most of the time we aren't going to do Kw because Kw is considered a negligible contributor. And so probably just only Ka if we're interested in pH. But what if we have ammonium acetate? Ammonium acetate. Yeah. Yeah, in order to do this qualitatively, we have to compare their Ks. And so the K for ammonium, the Ka is 10 to the minus 10. The Kb is, for acetate, is about 10 to the minus 10. And so it turns out that I'm going to generate some hydronium, and I'm going to generate some hydroxide, but they're approximately equal. And so the Ks are going to be about the same. And so this is the way it's going to work. If Ka, this is a mix. If Ka is about comparable to Kb in terms of magnitude, then the pH is about 7. If Ka is dominant, that is Ka is greater than Kb, then the pH should be less than 7. We generate more hydronium than hydroxide. If the Kb is greater, then we generate more hydroxide, and the pH goes above 7. How would we solve this quantitatively? Yeah, we have to do Ka for ammonium and Kb for acetate. This is going to generate hydronium, this is going to generate hydroxide. And what ties together those two would be Kw. In other words, we would have to do you guys see this, or should I? It has to be done simultaneous. Okay. We would have to do these because this scenario turns out to be just like the amphoteric. Remember the amphoteric species we did dihydrogen phosphate, we did the Ka and then we did the Kb, and we saw that Kw is going to perturb both of them. Well, the same thing's going to happen here. The only difference is these aren't the same species. Since they aren't the same species, then we don't have a simple equation to figure out what the pH is. And so quantitative for this is not done.
What would you use, like metric?
No, we wouldn't solve it. We aren't going to solve that. It's too hard for us. It's beyond the scope of this class. Right? And so we don't solve it. That doesn't mean all mixtures we give up like this. This is scenario A. Okay, scenario B, we have a mix, and it's the same species. And so this would be amphoteric, like dihydrogen phosphate. Dihydrogen phosphate, this has a Ka and a Kb. Then we compare. You know, for qualitative, it turns out that Ka is greater than Kb, therefore the pH is less than 7. So, for quantitative, then we have to solve this simultaneous, but in other words, it's the exact same thing. We got Ka for H2PO4 minus, got to do that. And then we got to do Kb for H2PO4 minus. And Kw. If we do one and then another, we'll see it's going to perturb, right? And we're going to be in trouble. And so there's a bunch of math involved here that we don't have to do. And ultimately, we get a very simple equation. The pH is equal to the pKa for the amphoteric, plus the pKa for the conjugate acid of the amphoteric, divided by 2. So yes, you're supposed to solve it simultaneously, but we don't have to. We just use this equation. Where did that equation come from? Well, somebody else did all the math. Are you going to have to derive that equation? No, you don't have to derive that equation because it's too much work. And so if the mixture consists of an acid and a base that are identical to each other, then we're lucky. We have that. There's one more scenario here. Let's see. If the mix is not the same species, but has an acid and a base that are conjugates of each other. And so an example of that would be this. If we have H2PO4 minus and HPO4 2 minus. Maybe this one's complicated, but do you see that these are conjugates of each other? Now, this one's complicated because both of these species are amphoteric. But in the context of this, H2PO4 minus is both an acid and a base. So which way is it going to behave? Is it going to behave as the acid or is it going to behave as the base? And HPO4 2 minus is the same thing. But when you combine them together like this, then H2PO4 minus will be an acid, and HPO4 2 minus will be the base. And so their identities will be fixed in the mixture because this is the strongest acid present, that's the strongest base. And so here, we're going to have a Ka for this one and a Kb for this one. Here, again, it looks like we would have to solve this simultaneously, but these two are related. And all we have to do is one or the other. In other words, for quantitative, we're going to have another very simple equation. The simple equation is going to look like this, that the pH is equal to the pKa plus the log of the base to acid ratio. And so that saves us some work. This one is not hard. This one we don't have to solve simultaneous. We'll see that. But we're going to get into this one soon. This is called a Henderson-Hasselbalch buffer solution. Henderson-Hasselbalch buffer. And so some solutions are pretty easy. Let's look at some examples. Aluminum chloride. What's the pH going to be for aluminum chloride? Acidic, basic, or neutral? Acidic. If you want to do a quantitative pH calculation, you just look at the Ka for aluminum, 3+ on the chart. And so this is acidic. Look at the next one here. Potassium chloride. Neutral. It's pH 7. Neutral is going to be pH 7. Potassium sulfate. Potassium sulfate. Basic. You could look it up on the chart. Sulfate's a base over there. Let me do this one. This one here, this is basic. But you know, sulfate ion is what we call a dibasic base. And so a dibasic base is going to have a Kb1 and a Kb2. Something like phosphate, you know, PO43 minus is a tribasic base. Dibasic base is capable of accepting 2 protons. A tribasic base is capable of accepting 3 protons. So let's take a look. If I wanted to do this quantitatively, how would I do it? Well, I would do this. You know, I'd have a step 1. Step 1 is sulfate, hydrolyzes water to form HSO4 minus and hydroxide. So I would look, you know, this would be KB1. KB1 is equal to KB for sulfate ion. And this would be KB1 for sulfate, which is going to equal Kw divided by Ka for HSO4 minus. So this is 1.0 times 10 to the minus 14. I know HSO4 minus is Ka, it's 0.011. It gives it to me. So in step 1, I'm going to generate some hydroxide. And then I go to step 2. Step 2 is, well, this is a dibasic base, so that means HSO4 minus can collide with water to form H2SO4 plus some more hydroxide. And so this would be another hydroxide contributor. This would be Kb2. It would be Kb for HSO4 minus, which is Kw divided by the Ka for H2SO4. And then step 3 would be Kw. If I'm only interested in the pH, then most likely I just do step 1. Unless step 2 is big, but you know, what is the Ka for H2SO4 minus? Ka for H2SO4 minus, everybody should have that memorized because it's a strong acid. It's very large. And so that means Kb is going to be very small. Kb is very small. This is going to be a negligible contributor to hydroxide. If I wanted the inventory, though, I'd go through the steps, right? But I don't have a number here. And so, you know, sulfate is a base. Phosphate, you know, phosphate would have step 1, Kb1, step 2, Kb2, step 3, Kb3, and then Kw. Right? The same thing. All right. So that's the next one. Let's take a look. We'll do potassium, aluminum, sulfate. Potassium, aluminum, sulfate. Potassium ions, neutral. Aluminum, acidic, and sulfate is basic. And so here, qualitatively, we would look, you know, aluminum has a Ka 10 to the minus 5. Sulfate has a Kb. It's a Kb sulfate. 10 to the minus 14 divided by 10 to the minus 1. Minus 14 divided by 10 to the minus 1, 10 to the minus 2 would be about 10 to the minus 12 approximately. So the pH of this should be but we have twice as much sulfate, so we got to be careful. What do you think? Acidic, basic, or neutral? Acidic, yeah. And so the pH should be less than 7. This many orders of magnitude. Okay, how about quantitatively? So this is an acid-base mixture. How do we figure it out quantitatively? We'd have to do the Ka for aluminum, the Kb for sulfate, and Kw, which means simultaneous. Oh, Raheem, you have an announcement?
Okay, hi everybody. So, I didn't get to making a chapter 17 worksheet this weekend, so I'm just going to have this week's workshops, the 2 workshops on Tuesdays and Thursdays, to only cover chapter 16. So what I'm going to do is I'm going to do 1 or 2 problems for each session, and then I'm going to leave the discussion open to any questions you might have. Preferably, I do not want to see like you asking questions about like the homework. So like, oh, can you solve this homework problem for us? I don't want to deal with that. So just like come in with questions like related to concepts that'll help you get through the homework problems, hopefully. Okay? So if you have questions on your homework, I suggest you talk to Dr. Chabal maybe, but the workshop is supposed to enrich your learning, not be a solutions manual. So Tuesdays and Thursdays is chapter 16, so if anyone has any questions, ask them now. I'm gonna leave. Now I'll see you guys this week, and then we'll start chapter 17 next week. All right, good luck guys.
Thanks.
Bye.
All right, so basically this is going to be Ka, Kb, and Kw simultaneous. Unless it's one of the 2 scenarios that we saw. What were the 2 exceptions that we saw? If Ka and Kb are the same species. Are they the same species here? No. Or if they're conjugate pairs. Ka and Kb conjugate pairs? No. And so we can't solve this. So we're stuck. All right, this is going to feed into chapter 17. Chapter 17, we're looking at acid and base mixtures. Well, this is an acid, this is a base, this is a mixture. This is an acid-base mixture. When you mix an acid with a base, what's supposed to happen? What's supposed to happen is you're supposed to get acid-base neutralization. Do we get acid-base neutralization here? No, there's no acid-base neutralization here. What's happening? And so let's take a look at mixtures of weak acids and weak bases and see the possible scenarios that come up. This is chapter 17, looking at mixtures, acid-base mixtures. The first type of acid-base mixture we're looking at is weak and weak. Weak acid, weak base. All right, let's do a simple one. An example of this would be acetic acid plus ammonia. Acetic acid and ammonia. If you take acetic acid and ammonia and react it, what do you get? So what we want to do is, let's take a 0.100 molar of the acetic acid mixed with 0.100 molar of ammonia. And I'm going to ask you, what is the pH of this? pH is equal to what? After, it's neutralized. Is the pH going to be 7? The acid neutralizes the base? Turns out, no, it's not going to be 7. Or maybe it is, I don't know. We'll see. And so what's going to happen is this. Acetic acid reacts with ammonia to form what? Not water and salt. Normally, salt and water is what you memorize. Salt, but no. Yeah, we're going to form Well, acetate and ammonium. And so is it going to be complete? That is, if I take 0.100 molar acetic acid and 0.100 molar ammonia, is it going to be complete? I don't know. It depends on what K is. And so let's try to figure out what K is for this reaction. Where's K for the reaction? Let's try to figure, well, we don't know what K is for this reaction, but we can try to figure it out based on reactions that we do know. What are some reactions that we do know? Let's go with acetic acid. What's in a reaction that we do know for acetic acid that we have the K value for? Yeah. And so if we do acetic acid plus water, this is going to give us acetate plus hydronium. This is the Ka for acetic acid. Okay. And then ammonia, we do know that ammonia plus water would be the Kb equation. We have the Kb value. This is going to give us ammonium plus hydroxide. This is Kb. If we add up these two equations, then we have acetic acid, ammonia. We got two waters, acetate, ammonium. We got to get rid of the hydronium and hydroxide in the two waters. How can we do that? Well, we can add this equation. Hydronium plus hydroxide yields H2O liquid plus H2O liquid. You recognize that equation? That would be the reverse of Kw. And so K for this reaction is just equal to Ka for acetic acid, which I'll abbreviate HAC, plus the Kb for ammonia, H3, divided by Kw, 1.0 times 10 minus 14. And so we can figure out the K for this by doing that. The acetic acid, Ka, is 1.8 times 10 minus 5. Kb for ammonia just so happens to be the same number, 1.8 times 10 minus 5, but by random coincidence, not because they're connected in any way. This is going to be divided by 1.0 times 10 minus 14. If we were to carry it out more than 2 sig figs, it would be different. So now what? Well, let's figure out what this number is. What is K for the reaction? This is 1.8 times 10 minus 5 squared divided by 10 minus 14. You got 2.04 times 10 to the 4? Yeah? You got something else? 2.24? What did you get? 3.24? 3.24 times 10 to the 4th? Okay. Let's do that. Do you see, this is a good candidate for resetting. Why? If I didn't reset it, I'd just do the change, which is minus x plus x plus x. But the change is going to be big. Why is the change going to be big? Because K is big. I want to make the change as small as possible. One way to make the change as small as possible is to reset it to the right. If I reset this to the right and then let the reaction go to the left, then the change is going to be small. And so here, I would reset this. And so I end up with a new set of initial conditions: 0 molar, 0 molar, 0.100 molar, 0.100 molar. And so I'm just going to approach equilibrium from the right instead of the left. So this is going to be plus X molar, minus X molar, minus X molar. And so at equilibrium, I'll have X molar, 0.100, minus X molar, 0.100, minus X molar. The reason I want to reset it is so that I can use the simplifying assumption, because going forward is a big driving force, but going backwards, it isn't. So this is highly favored towards the product. Now, that being the case, I'm not going to lose that much product. So this is going to be 0.100 minus X squared divided by X squared. Actually, you know what? This one I don't even have to use the simplifying assumption, because I have a squared squared. So I've got a squared squared, just take the square root of both sides. Solve it. Or I can use the simplifying assumption. If I decide to use the simplifying assumptions, it should work here. But what does X come out to? Somebody have it? Actually, what time do we go till? 40? We only have 2 more minutes? 3 more minutes? 3 more minutes. Yeah, you can use a simplifying assumption, it'll work. 5.5 times 10 to the negative 10. Times 10 to the negative 4. 5.50. 5.52 times 10 to the negative 4. Okay, so going back over here, I'm going to have 5.54 times 10 to the negative 2 molar. 5.54 times 10 to the negative 2 molar. And then this is going to be 0.100 minus, oops, 5.52 times 10 to the negative 4. Thanks. This is going to be minus 0.123552. So we're going to lose about 0.5%. This is going to come out to 0.099448 molar. 0.099448. All right, so what do we do next? Can we figure out the pH right now? No, because there's no hydronium here. And so we gotta, something's gotta hydrolyze, so we gotta look for the hydronium ion contributors. And so in this mixture, what are the hydronium ion contributors? Acetic acid is a hydronium ion contributor, and ammonium. Acetic acid is a much better acid, but you look at the concentration is very small. So we look at the hydronium ion produced from ammonium. But then we would look at acetic acid, then we'd look at KW, but we also have hydroxide ion contributors. Do you see what we are left with? Take a look. If you ignore these two, what are we left with? We're left with a mixture of ammonium and acetate. How do we deal with ammonium and acetate? One is a Ka, the other is a Kb. So what should we do? Should we just do the Ka and ignore the Kb? We can't. They're both the same concentration. You know, we can't do the Kb. We have to do both. And so in this case, how do we do both? Simultaneous. So what we end up with here is a simultaneous equilibrium problem, ammonium and acetate, right? But we also have acetic acid and ammonia. But acetic acid and ammonia, we don't have to do two sets of simultaneous, right? In other words, we don't have 5 simultaneous ice that we have to solve because acetic acid is the conjugate of acetate, and so the acetic acid acetate equilibrium is already described in Kb. We don't need to do Ka for acetic acid because we have Kb for acetate going on. And the same thing, ammonia is a base, but we are already taking care of ammonium. And so what describes the ammonium-ammonia equilibrium is Ka for ammonia. If we did Kb for, Ka for ammonium, if we did Kb for ammonia, we'd get the same equilibrium just described in. And so we just look at one set of these, and it turns out it is going to be simultaneous. So the best we can do is say that the pH is going to be roughly 7 because, you know, both of these have about the same K. Okay. All right, so we'll do some more acid-base mixtures coming up.